Okay, we had been discussing basic transformer action. We actually said that when I am having a transformer which is represented basically by a ferromagnetic core, and on one side I have the primary winding and on the other side I have the secondary winding, right? And in the primary winding I am connecting a voltage source which is having a value of V1. This may draw a very small current which I am calling as I0, that is the no load current. That is the no load current which is establishing the flux in the core, and the core is made up of ferromagnetic material. The permeability is really high, because of which I0 is going to be low. Let's take for example some practical values. Let's say I am going to take a 2.2 kVA transformer, 220 by 110 volts. Okay. So the primary side current, full load current or rated current will be 2200 divided by 220, which is about 10 ampere, and secondary current full load will be 110 divided by 20 amperes, 2200 divided by 110, which will be 20 amperes. So I should say in all probability I should be connecting a load of 5.5 ohms on the secondary side. 110 divided by 5.5 will give me 20 amperes of current, right? So if I am looking at the no load condition current will be of the order of 0.2 or 0.3 amperes, nothing more than that, from the primary side. I am talking about the primary side, right? So from the primary side, this is all will be the current. When this flux is established, I am going to have the secondary voltage which will be induced across this winding, which will amount to 110 volts on open circuit condition. Now I am going to connect a load here like this. So this is 5.5 ohm. I am connecting a 5.5 ohm load. So what is going to happen is a current will flow here which will be corresponding to I2, which we wrote as 20 amperes if I am connecting 5.5 ohm. So this 20 ampere will create definitely a flux in the core. It is not going to keep quiet. It is going to create a flux in the core. But this flux in the core should oppose the original flux. If it had been aiding the original flux, it will go to extremely large values and d phi by dt will also reach literally infinity. So obviously by Lenz's law, this has to oppose the original flux. The original flux was in this direction. It was actually going like this. This is what was phi m, or the mutual flux between the primary and secondary coils. Now the new flux that has come up will oppose this, and because the ampere turns of this new flux will be quite high. Originally I had only 0.2 amperes of current with N1, whatever be the number of turns, N1B. Let's say maybe I had 200 turns here and 100 turns here. So N1 equal to 200, N2 equal to 100. I am just taking it like this. So I am going to have an ampere turn which is way too high as compared to the original ampere turn. So it will essentially kill that. If that is being killed, the entire transformer action will cease to exist. So what is going to happen is, if the transformer action ceases to exist, I would have had definitely an E1 induced here as well. That E1 will also collapse. If E1 collapses, I will have definitely a huge current that will be flowing into the primary winding, because originally what was running was V1 minus E1 divided by the resistance of the primary coil. That is what was actually making the current go, right? Originally V1 was equal to E1, especially under no load condition. There is no drop also because the current was only 0.3 ampere. So the drop was negligible. So I was having basically V1 is equal to E1. But now if the flux collapses even for a fraction of a microsecond or millisecond, I'm going to have definitely the EMF also collapsing, huge current will flow. So that current, what is being established in the primary, will be rather gushing to such a value in such a way that you are going to have the ampere turns created by the secondary will be completely balanced by the ampere turns that have come up in the primary, suddenly. So I am essentially going to have I1, originally it was I0, now I am going to have I1, and I am going to have essentially I1 N1 is equal to I2 N2. I2 N2 was the new ampere turns that were created because of the load current, and I1 N1 is the current where the primary has essentially drawn excessive amount of current to make sure that I2 N2 is nullified. So I1 N1 and I2 N2 are equal to each other but opposite in opposite directions, because of which I'm going to have only the original flux, which was phi m, that will prevail. That will be maintained. So the transformer action is maintained because of the mutual flux, which was originally established with the help of the no load current. After that, whatever is the current drawn due to load being included, that will always be nullified by whatever is the current that is drawn from the primary, to make sure that that particular, the ampere turn is quelled completely. That is what is going to be happening. So if I look at the values, I am going to have 20 amperes as the secondary side current. So corresponding primary side current will be 10 ampere. If I look at the total current of the primary side, I should have this 10 ampere added to the 0.3 or 0.2 amperes with their respective power factors as well. So definitely it will not be even 10.2 or 10.3. It will be 10 square plus whatever is, 0.2 square, along with their own power factor angles and so on and so forth. That is what will be the total current. And the total current definitely will be very, very close to 10. So I can literally neglect I0. That is the reason why, if I have to be really, really accurate, I should say I2, I1 N1 plus I0 N1 as well. I should have said this. But I am essentially neglecting this because when I add I0 and I1 along with their phase angles, the overall current what I get will be almost equal to I1 itself. It is not going to be any different from that of I1, which we will see eventually when we are drawing the phasor diagram. Right? Is this clear? So the ampere turn balance essentially is the major underlying principle of transformer action. We will revisit this for every kind of transformer that we are going to talk about. So we have seen basically that the transformer is going to follow V1 by V2 equal to N1 by N2 equal to I2 by I1. This is the relationship that is going to be followed by the transformer. Let us start off with ideal transformer action, and then let us go over to the actual practical transformer. So in an ideal transformer, right, I'm going to again specify that by a core, and then I'm going to have one winding here, which is the primary, and I'm going to apply a voltage of V1 here, and I1 is flowing here after the load is connected, of course, and I'm going to have the secondary winding here, and I'm going to have V2 as the terminal voltage. I have still not shown the load. So we are going to have basically, in an ideal transformer, we are going to neglect a few things. What are all the assumptions that we are going to make? Because obviously practical transformer will differ from this. Okay? So the first and foremost assumption we are going to make is the windings have no resistance. So we are going to assume that the conductors are ideal. So I'm not going to have any voltage drop inside those winding resistances. The resistances are assumed to be 0. So I'm going to assume that the windings have no resistance. The second assumption that I'm going to make is that if I want to establish a flux in the transformer, I will require literally 0 current if the permeability is infinity. So I'm going to assume that the permeability is infinity. So permeability of the core is infinity. Right? Third assumption that I'm going to make is that the core is not going to have any losses. So if I say permeability is infinity, very clearly I'm going to have the magnetizing current equal to 0. This is implied. I'm not going to draw any current to magnetize the core or establish the flux. So I'm assuming that magnetizing current is 0. The third assumption I am making is the core losses are 0. I'm not going to have any losses in the core. And the last assumption that I'm going to make is whatever is the flux established, that is going to completely confine itself to the core. That means nothing is going to flow through the air surrounding it. So whatever flux links with the primary will always link with the secondary and vice versa. So leakage is 0. I don't have any leakage at all. Right? So if I assume that there is no resistance and there are no core losses, very clearly I'm going to have whatever is the input power is equal to the output power. So I should be able to write basically V1 I1 equal to V2 I2. That's it. Right? So this is one way of saying V1 by V2 equal to I2 by I1. But definitely it is not as enlightening as what we talked about in the case of ampere turn balance. Because the transformers normally have as high an efficiency as 98% or 99% in many cases. Which means I can say almost all the input power is converted into output power. So which means the assumptions what we have made as resistance is negligible or very, very small is true. No doubt. But it's not 0. Definitely it's not 0. That's the reason why you are getting the efficiency to be 98% or 99%. Otherwise you should have had the efficiency to be 100%. Right? Now let us say I have connected a resistance here or a impedance. Let me call this as ZL. So I have connected a load impedance of ZL. When I connect the load impedance of ZL, right, this is going to probably draw a current of, let us say, I2. Right? Now I can say the power on the secondary side is V2 I2, whatever is cos phi 2. If I say Z2 is purely resistive, I can directly say V2 I2 is the power. And V2 I2 equal to V1 I1 if I neglect all the losses, from which I can definitely say this is true. Right. Now I would like to represent this ZL on the primary side, or I want to transfer the impedance from the secondary side to the primary side. So if I want to find out what is the equivalent load impedance on the primary side. So I want to transfer the impedance. So I have to see how I do it. So I want to see what is the load on the primary side. For that, what I have to do is, Let me call that as ZL dash probably, because ZL is the actual impedance connected on the secondary side. ZL dash is the equivalent impedance I am visualizing from the primary side. That should be equal to V1 by I1. Right? Only then I will call it as the equivalent impedance as I visualize from the primary side. But V1, we wrote already V1 by V2 equal to N1 by N2. So I should be able to write this V1 as V2 multiplied by N1 by N2. Right? And similarly, I can write this I1 in terms of I2. So I should be able to write this as I1 equal to I2 divided by N1 by N2. So I can say I2 multiplied by again N1 by N2, I am taking it here. Right? Now V2 by I2 is actually my ZL. Right? That's what we wrote earlier. V2 by I2 is ZL. So I should be able to write ZL multiplied by N1 by N2, the whole square will be ZL dash. So if I represent the load impedance connected on the secondary side of the transformer from the primary side, as visualized from the primary side, I have to essentially multiply that by the turns ratio square. And to whichever side I am transferring it, that number of turns should come in the numerator. The other one should come in the denominator. You can remember it that way. Basically, we are looking at the impedance being transferred from one side to the other side. To whichever side, the destination side, should be coming on the numerator. The number of turns of the destination side should come on the numerator. And from where I am transferring should come on the denominator. So I should have N1 by N2 whole square as the transfer parameter when I am trying to transfer the impedance from the secondary side into the primary side. Fine? So I should be able to draw it somewhat like this. If this is my primary side, this is what was V1. Originally I had one winding here, another winding here, and here is V2, and I had connected ZL here. This is what was the representation of the transformer. Now I should be able to write this directly as though I just have V1 applied here. I don't have to represent them by two different windings and so on and so forth. I can simply draw an impedance here, which is ZL dash. And I'm going to have a current of I1 flowing here. Whereas here, of course, it was I2 and here it was I1. This is how it was. So we have just represented this by a single circuit, and this is definitely easier for applying KVL, KCL and so on. That's the reason we wanted to eliminate this magnetically coupled, representation. Fine? Now let us try to take a look at a practical transformer. We said we are neglecting the resistance in the primary and secondary windings. The first and foremost thing we are going to do is to include, so let us say primary winding resistance. Let me take that as some R1, and secondary resistance I am going to take as R2. Okay? So I have taken both the resistances. Now, the next thing that we need to consider, so let me look at the transformer again. I have here is the winding and I have a resistance here, which is R1. Right? Similarly, I have the secondary here and I have a resistance of R2. We have still not completed the circuit. When I have the flux established, as I told you earlier when we were discussing the magnetic circuits, there will be definitely, say, thousands of lines that are flowing through the electromagnetic core. At least one or two will escape and they will go through the air gap path. So if I am saying that I have probably this as the core and I have got primary winding here and the secondary winding here, although most of the flux will go like this, maybe one or two of flux lines will go like this and go like this. These are leakage flux lines as far as the primary is concerned. Similarly, I will have at least some flux lines go here like this and go here like this. So these are going to be the leakage flux lines corresponding to secondary. Practically, we would never ever construct a transformer like this. The primary on one side and secondary on other side. Even if I am saying that this is what is my core and I am going to have probably the primary here and one more secondary coming up here and so on, still the lines of flux can go only through this. It doesn't have to link the secondary. Who knows? In which case, there will be still some amount of leakage flux. But in general, what I can say is the leakage is invariably through the air path. It is hardly ever through the ion path. It is going to be always through the air path. Because it is through the air path, definitely it is going to cause some self-induced EMF. That self-induced EMF will account for some kind of inductive drop. So I would always represent the voltage that is lost, the self-induced EMF that is lost in the form of leakage parameter. I would rather represent that by an inductance drop, which is known as the leakage inductance drop or leakage reactance drop. So if I may call this leakage reactance for the primary as LL1 leakage, similarly LL2 is the leakage corresponding to the secondary side, I can definitely say that this LL1 will be corresponding to the number of turns. N phi by I is inductance, right? So I can say this is N1 multiplied by whatever is the leakage flux corresponding to the primary divided by I1 or small I1, whatever, right? Similarly, I should be able to say this as N2 multiplied by phi L2 divided by I2 or small I2 instantaneously if I try to calculate. So this is going to be my leakage inductances. One thing I want you to realize is I can represent the same thing by N square by reluctance as well. We derived one expression for inductance. So I should be able to write this as N1 square divided by the reluctance of the primary air gap path. Similarly, for the other case, it will be N2 square by R2, where R2 will correspond to the secondary air gap reluctance path. And please remember that this reluctance is along the air gap. So that is not going to change. If the reluctance in the iron core we are considering, the permeability keeps on changing depending upon at what portion of the magnetization characteristics we are operating the machine, right? So the permeability is not a constant in the case of a ferromagnetic core. So the inductance will not be a constant depending upon the magnetization characteristics portion where we are operating. So if I consider the air gap, this is essentially air gap reluctance. This is air gap reluctance. So I am essentially going to have this as a constant. This will not change. So if I am assuming this to be a constant, I can say the leakage inductance is also fairly a constant. It is not going to change. The leakage inductance will not change in the case of a transformer. So I would say that LL1 and LL2, they are not equal to each other. LL1 comma LL2, they need not be equal to each other, are constants as far as the transformer is concerned. So they can be represented as inductances which are coming in series with this winding. Similarly, I can put one more inductance in series on the other side. Let me call this as LL1. Let me call this as LL2. Right? Now, of course, I'll be applying a voltage V1 here. And I will be connecting a load ZL here. Right? Now, whatever is available as V1, I'm going to say that if this is drawing a current of I2, this may be a current corresponding to I1, which will be actually governed by the turns ratio. Right? I1 should be actually governed by the turns ratio because I1 by I2 will be equal to N2 by N1. Now, if this is I1, I'm going to have V1 minus I1 times R1 plus JXL1. That is what is going to be available as E1 here. Right? So what is available as the induced EMF, which is actually giving me the relationship finally E1 by E2 equal to, N1 by N2. So E1 I am talking about as the available EMF across the winding, which will be actually inducing a secondary EMF. So I am going to write E1 by E2 equal to N1 by N2. If I am writing in terms of even instantaneous voltages. So, I would definitely have only E1 available across the primary winding, which will be instrumental in inducing a secondary EMF of E2. So, the magnetic flux that is established in the core will correspond to E1 and not correspond to V1. I hope you understand. V1 is the applied voltage. E1 is the voltage that is induced within the primary coil, which will be linking with the secondary coil as well. So obviously E1 will be less than V1, and it will be essentially because of the drop that occurs in the leakage reactance and the resistance of the primary winding. Right? Now, this is essentially the voltage that is available in the secondary, E2. So, from E2, again I should have I2 times R2 plus JXL2 dropping, and rest of what is available will be the terminal voltage. So, I am going to have the terminal voltage V2 or what is available across the load. This is also V load. The same voltage is V load. So V load clearly is less than E2. So I have two sets of drops, voltage drops. One is in the primary resistance and leakage reactance. Another one is secondary resistance and leakage reactance. Only after both these drops, whatever is available goes to the load. How much ever negligible it may be, but when we actually calculate this for thousands of amperes of current, although the resistance may be only 0.1 ohm or 0.01 ohms, still it adds up and it comes to somewhat not such a negligible value. So we have to take care of that. Now that we have said that, this E1 is the one which is corresponding to the flux established. That flux is the one which causes core losses. And the flux is established because of the magnetizing current which would have flown even under no load condition. So I have to represent them as well. So those will be represented just like what we did in the case of magnetic circuit analysis for sinusoidal excitation. So please recall that, and for that how we represented was to have a resistance and a magnetizing reactance which would come parallel with each other for whatever is the voltage that is coming up across this. And the voltage that is coming up in this case is E1 and not V1. That's not V1, that is E1, because the flux is established, the mutual flux is established corresponding to the self-induced EMF within the primary coil, which is linking with the secondary coil as well. The leakage definitely does not link with the secondary coil. So I have to necessarily subtract R1 and XL1 drop before I really say that this is what is the established EMF in the primary which is linking with the secondary. Right? So this value of voltage will be E1. This resistance, what I am showing as RC, is a fictitious resistance. You can't put a multimeter and measure the core resistance and say that is what is RC. No, not at all. This is essentially due to the hysteresis losses and eddy current losses that take place within the core. So if that is so many watts, X watts or Y watts, we are essentially trying to negotiate or ultimately arrive at some value of resistance which would be representing this amount of loss. So this is a fictitious resistance, and similarly this reactance is also a fictitious reactance. So if I say this Xm is equal to 2 pi f Lm, right? That's what I would say as Xm. Now Lm can also be represented by N1 multiplied by phi m divided by the magnetizing current. I hope you understand. I can definitely write this as, because this was the original flux established when magnetizing current itself was flowing. It's not after I2 or I1 has come into picture. So I should be able to write this Lm as N1 multiplied by phi m divided by Im, or the magnetizing current. And this magnetizing current, what I am drawing to establish the flux, depends heavily upon in what portion of the magnetization characteristics I am working on, or the machine is working on. So obviously this Lm will not be a constant. For any voltage or any frequency, I can't say it will be a constant. It is difficult to say that it will be a constant unless I specify a particular operating point. If I say this is the operating point at which I am going to operate my transformer upon, let's try to look at again the magnetization characteristics and establish this. Let's say this is my magnetization characteristics. I am not showing the entire hysteresis loop. I am only showing the magnetization characteristics. And I am saying that this is Im and this is phi m. I can operate it here, I can operate it here, I can operate it here. Very clearly the inductance values will be different in different points. I can't say it will be the same. But invariably what we are actually doing is to operate this at rated voltage and rated frequency. Phi m is the mutual flux which is linking both primary and secondary, which is confining itself to the core. It is just confining itself to the core. So because of which it doesn't account for the leakage. The leakage is eliminated. Right? Im is the magnetizing current drawn by the transformer even under no load condition to establish the flux. So initially I am just applying a voltage V1. the transformer primary winding is energized. When it is energized, it is going to establish a flux. That flux established is phi m. That is confining itself to the core. And the secondary winding is linked with that flux, because of which you are going to get a voltage V2 induced. Right? So phi m essentially is not because I1 or I2, it is because of Im. And that is persistent. That is not going to be killed. Right? Because I2 was trying to kill it, and I1 bounced back to protect it. So you are having phi m all the time, and that is essentially the mutual flux which is linking both the primary and secondary. Now, depending upon the operating point, because I am talking about the mutual flux which is established in the ferromagnetic core, I have to take the magnetization characteristics of a ferromagnetic core. And if I am looking at different operating points, the inductance Lm will be different, no doubt. But if I am following basically this particular operating point of, let us say it's a 220 volts transformer, you know this equation, F multiplied by phi multiplied by number of turns, N1, if I talk about E1. Very clearly, for a given voltage and a given frequency, my flux is fixed. It cannot change, because it is essentially E1 divided by 4.44 divided by frequency, right, divided by the number of turns. It is set in stone. Once that is set in stone, I know for sure that I am going to operate at some particular operating point, nothing else. Okay? You got the point that Xm is 2 pi f Lm? No. Okay. Basically, we are establishing a flux in the core. So, in the core, we are establishing a flux. To establish a flux in the core, we need some current called magnetizing current if the permeability is not infinity. Right? So, you need some amount of current. And that current flowing through the coil wound around the core is establishing the flux. This can be represented by an inductance. That's what we said in the sinusoidal excitation when we were discussing, because the current is slightly lagging and we should be able to say that it will flow through essentially an inductance. So we are representing the magnetizing current flowing path by an inductance. This inductance we are calling as the magnetizing inductance, or Xm or Lm. 2 pi f Lm is the magnetizing reactance, which is Xm. Fine? So we are going back to the original discussion, or I want you to refer back to the original discussion what we did for a ferromagnetic core having an equivalent circuit of resistance in parallel with an inductance. The resistance is representing the core losses. The inductance is representing the current carried to establish a flux. Yeah. Im is almost same as I naught. I am going to come to that. Im is almost same as I naught. Please remember that I have also shown one more parallel path. The parallel path is definitely not talking about only inductive current. It is talking about a resistive current. So when I add the resistive current corresponding to core losses with that of the inductive current, which is magnetizing current, I get the total I naught. So under no load condition itself, I will have definitely core losses. That is represented by RC. I will also have the flux established. That is represented by Xm. So I have two portions of the no load current. One is in phase or real component. The other one is going to be the perpendicular component. So I will have two components definitely for the no load condition itself. So I do have now, does it make clear now? Can I go to the next slide? Okay. So we said that the voltage rating of a transformer is fixed, and similarly the frequency of a transformer is fixed. So this flux value is fixed. I would say, rather than saying flux value is fixed, nominal flux value is fixed. Because we say nominal voltage is this, nominal frequency is this, and nominal flux value is fixed. If nominal flux value is fixed, clearly I will have the magnetizing current also fixed. And the operating point is fixed, which means the inductance is fixed. So at rated condition or rated operating condition, we are going to have Lm value as a fixed value. It will not be changing. But if I try to plot Lm for different values of voltages, clearly the operating point is changing because E equal to 4.44 F phi N1. Phi will definitely change if I change the voltage. So if I try to plot what is the magnetizing reactance for different values of applied voltages, it would not be a constant. It would be changing. But for a given rating of the transformer, for a given operating point of the transformer, Lm will be a constant. Right? Now, we can draw the equivalent circuit as now R1, which is the primary winding resistance. Let me write this as small x1, which will actually correspond to the leakage reactance of the transformer primary winding. So rather than writing capital X L1 and so on, I am writing this as small x1. Fine? And I am going to have the primary winding here. Obviously, the resistance is spread out throughout the primary winding. Similarly, the leakage is not lumped in one place, but I am just lumping it so that it is easier for me to analyze the transformer. The resistance R1 is the lumped resistance of the primary winding. So I am lumping it together so that it is easy for me to analyze the whole thing. That's it. So this is primary winding resistance. Now what is available here is E1. Right? Now there is iron core here, and then I am going to have the secondary winding here. Now I am going to have secondary winding resistance, secondary winding leakage reactance, right? That is X2, and then here is the load. Now this portion I am going to represent by what we drew as the equivalent circuit of our ferromagnetic core. Right? So I have to fix this portion in the middle. But I am assuming that I am exciting the transformer from the primary side, and I am connecting the load on the secondary side. So I should show even this parallel component, whatever I am showing, in the primary side itself. Right? Although you can show it on either side, not a problem. But I am showing it on the primary side. So I would rather erase this portion. I would erase this portion and I would show it as though, so I am connecting basically one resistance and one inductance here. Right? And now I will show the primary winding as an ideal primary winding. Right? And similarly, secondary winding, let me show as an ideal secondary winding with the core in between. Got it? So what I am trying to do is to lump the non-idealities of the transformer in the form of a resistance, inductance in series, and the core losses and the magnetizing current requirement of the core to establish the flux and to feed the losses as RC and XM, again on the primary side itself. And what is left over in the form of the primary winding, which is shown here, is the idealized form of primary winding. As simple as that. Right? Now I can transfer these things to the other side. R2 and X2 and ZL, I should be able to transfer over to the primary side. If you want to show it on the other side, you have to again say RC multiplied by N2 by N1 the whole square. N2 by N1 the whole square has to be multiplied for each of the parameters. But normally we show it on the primary side because of the fact that we assume the excitation is always coming from the primary side and the load is always connected on the secondary side. This is our assumption, as simple as that. Yeah. Yeah. So in the parallel circuit, if I try to look at the current, I am going to have something as the core loss component of current. Fictitious, again. See, basically I am saying that maybe the hysteresis loss is something like 100 watts in a 2.2 kilowatt transformer, kVA transformer. Let's say it's 100 watts. Now what I have to write is, this 100 watts should be equal to IC square RC. Okay? And I am going to have certain flux established because of this magnetizing current. So that should also be whatever is my reluctance of the entire core I calculate and so on. I should have N1 times Im divided by the flux is the reluctance of the core. That is how it should come up. So now this is Im and this is IC. Please note that one is resistive current, one is inductive current. So if I show this as the voltage applied to the transformer, for example, I am going to have actually whatever is my IC somewhat like this, which will be in phase because it is resistive current, right? And I am going to have the other current as inductive. So I should show maybe my inductive current somewhat like this. I am drawing all big things. Really the currents are very small, but nevertheless, I am just showing it for the sake of it. Normally the core loss component of current will be much smaller than the magnetizing current. The core loss component is smaller because of the fact that the eddy current losses are minimized drastically by laminating the core. Hysteresis losses still exist. I can't eliminate. But the eddy current losses are minimized to a large extent because of the lamination process of the core. Okay? So now when I add them together, right, these two are added together. So I'm going to get this as I naught. That is what is my no load current. So the no load current of a transformer consists of two portions. One will correspond to core loss component of current, which is fictitious. And the other one is the magnetizing current drawn by the transformer, which I would not say is completely fictitious because you need that MMF definitely to establish the flux. But only because you establish the flux, the core loss is also happening. So if you measure, it will definitely consist of both real portion as well as reactive portion. That's why the no load current of the transformer will not lag behind the voltage exactly by 90 degrees. No way. It will definitely lag behind the voltage, all right, maybe by 80 degrees, maybe by 75 degrees, not 90 degrees. This is essentially because of the core losses is real. It is happening. You can't negate it, right? So this is the phasor diagram corresponding to no load condition. This is the no load phasor diagram, right? Now I hope so that you have at least gotten an idea of how really the transformer functioning is built up, right from the no load condition. Then you connect the load, then the current bounces back, and that current what comes here. So if I call this as I2, I should say definitely there is no load current here. There will be definitely I2 dash or whatever is the reflected current from the secondary side into the primary. Now I2 dash and I naught together makes up for I1. Of course, I naught is really small. That's why we were able to neglect it. We wrote V1 I1 equal to V2 I2. We are neglecting I naught, but if I want accuracy, I cannot neglect I naught. Right? Is this clear? So what we are having is essentially a load current on the secondary side that will have a reflection on the primary side. And the primary side reflection will have the same power factor as that of the load power factor. There is no difference because I have not included the no load current as yet. No load current definitely will have a very poor power factor because it consists of a magnetizing current and it consists of a core loss component of current. And core loss component of current is minimal because I have already laminated the core. But the magnetizing current is, if I look at the comparison, if I have 0.3 amperes as the overall current, as the no load current, I may have 0.05 ampere probably as the core loss component of current. Whereas almost closer to 0.28 or 0.25, 0.27 something as my magnetizing component of current. So when I add them, I have to say IC is the real component of current. So the no load current will become IC plus J or minus J. It is minus J. Minus J IM. Please look at it as a complex number again. I have the core loss component of current which is in the real axis along the positive direction, whereas magnetizing current is in the imaginary axis along the negative direction. This is my no load current. Is that clear? Now to this, if I want to get what is actually I1, I have to write I1 will be equal to this I0, I am writing this as a vector, plus whatever is my I2 dash. This is also a vector. Both of them are vectors. Are you getting my point? So let me just finish by drawing the overall equivalent circuit from which we will start off our discussion tomorrow. So I am going to have R1, I am going to have X1, and I am having here RC and XM, right? And on the secondary side, I am going to have R2 dash, X2 dash, and ZL dash. What I am applying is V1. What I am getting here is E1. I can also call that as E2 dash. No harm in saying that, right? E2 dash is actually E2 multiplied by N1 by N2. Everywhere you put the turns ratio. Basically what we have is E1 by E2 equal to N1 by N2. Right? So I am going to write this E2 dash is actually same as E1. Both of them are the same. So how can I say that? It is because it is N1 by N2 into E2. I am transferring over the secondary voltage onto the primary side. So we will continue from this point onwards in tomorrow's class.